Hello everyone. Let us discuss about the analysis of trusses today. I have already discussed the stiffness matrix of truss. Let us review it. So, a truss is a one-dimensional element. One-dimensional element. It is a structural member consisting of n number of link elements connected together in order to form a structural element. So in general, in local coordinate system, a truss is equivalent to a bar element. But in global coordinate system, a truss is consisting of two nodes at each, two degree of freedom at each node. So, totally, if you consider a single truss element in global coordinate, then there will be two nodes with the 2 degree of freedom at each node. So overall, there will be 4 degree of freedom system for a single link element when it is considered in global coordinate system. So let us have the derivation of elemental stiffness matrix for the truss. For this, we require the stiffness matrix of bar. So the stiffness matrix of bar is K is equals to AE by L in the matrix of 1 minus 1 minus 1 1. So in local coordinate system, as truss is equivalent to bar, so the stiffness matrix of truss in local coordinate system you can consider as K is equals to AE by L in the matrix of 1 minus 1 minus 1 1. So so in global coordinate system, uh, the truss is considered to be a two-dimensional element. So each node will be having displacement along x and y direction. So totally there will be 4 degrees of freedom system. So I have considered here a single truss element. So it is one element. So in local coordinate system, local we are representing in terms of x dash here. So consisting of two nodes with the displacements q1 dash and q2 dash only when it is considered along x dash direction. So if the same element, if it is considered with respect to global coordinate in xy coordinate system, then node 1 can displace along x and y direction and node 2 also displace along x and y direction. So the displacements of this element in global coordinate system will be q1 and q2 and q3 and q4 with respect to the node number 2. So in order to have the stiffness matrix of this truss element in global coordinate system, let us consider the strain energy, which is given by half q transpose k into q, where as the dash terms represents the local coordinate system. So I can write this strain energy as half q dash transpose k dash into q dash. So where k dash is stiffness matrix of truss in local coordinate system, and the uh, uh, q dash transpose and q dash are the nodal displacement vector with respect to local coordinate system. So the requirement here is to uh, uh, it is required to convert the local displacements to global coordinate system by uh, by uh, by transforming the local displacements to the global displacements. So we can write this q dash as L into q, where q dash is a displacement vector in local coordinate system, and this so L is a transformation matrix. So let us substitute let us substitute L as cos theta sin theta 0 0 0 0 and sin theta cos theta, which is nothing but Lm 0 0 0 0 Lm. So as q dash is to be transposed is to be transferred along q and q1 direction. So it will be q1 cos theta and q2 sin theta. Similarly, q2 is to be transferred to along q3 and q4 direction. So it will be q3 cos theta and q4 sin theta. So the same thing I have written here. L is equals to cos theta sin theta 0 0 and 0 0 sin theta cos theta with respect to q1, q2, q3, q4, and in the second row also with respect to q1, q2, q3, q4. So it is nothing but Lm 0 0 0 0 L. So therefore, substituting the terms of q dash and q Q dash transpose and Q dash. So therefore, strain energy will be equals to half Q transpose and Q transpose. It will be L transpose to K dash L into Q. So it will be half Q transpose K into Q, or K is equals to L transpose K dash into L is the stiffness matrix of truss element in global coordinate system. So where L transpose is the transpose of the transformation matrix, K dash is the stiffness matrix of truss in local coordinate system, and L is again it is the transformation matrix. So if we multiply these three matrices together, first the transpose of L to the stiffness matrix in local coordinate, then the resultant with respect to the transformation matrix. So we'll get Ke as Ae by Le in the matrix of L square Lm minus L square minus Lm Lm m square minus Lm minus m square minus L square minus Lm L square Lm and minus Lm minus m square Lm and m square. So it is the stiffness matrix of the truss element in global coordinate system, where L is representing the cos theta, which is nothing but x final minus x initial divided by length of element, and M is nothing but sin theta, which is y final minus y initial divided by length of element. And L is nothing but the length of element, which you can either consider as straight away if it is along horizontal and vertical direction. The link is along horizontal and vertical direction. You can consider the length as it is. So if it is diagonal link, then LE will be equals to square root of x final minus x initial whole square plus y final minus y initial whole square. So this represents the stiffness matrix of the truss element. So